In this unit, we'll discuss reinforced concrete design in the context of gravity anchors. The governing code for our analysis will be ACI 318-14, Building Code Requirements for Structural Concrete, which we will use to guide stability checks for flexural capacity, shear capacity, and bearing capacity, along with conformance to the requirements for the placing and detailing of reinforcement. The learning objectives for this module are as follows. First, we want to understand how to navigate the ACI 318 code. Second, we want to analyze a reinforced concrete beam for adequate strength. Third, we want to interpret code requirements for reinforcement placement and detailing. And fourth, we want to learn how to employ the LRFD, the load reduction factor design method for reinforced concrete design. But first, we need to set up our problem. And throughout this lecture, we will use the medium anchor, or the A2 anchor detail, as our example. So in the following diagram on the left, we'll estimate the beam section formed by the largest rectangle you can draw perpendicular to the loading. We'll call W effective as the section width, and D effective the section depth. H anchor is the anchor height, and B1 is the width at the top of the anchor, as called out in the details. We have theta prime as the offset angle at the front of the anchor, which is the rotational offset of the entire section from our normal XY coordinate plane. So moving to the right, I've drawn an isometric view of the anchor showing forces from earth pressure and cable load acting on the anchor beam, bearing on the masonry wall supports of the minimum 30 centimeter overlap. The plan view shows the unbraced span of 240 centimeters, and a quick note here, eventually the fill does partially brace the anchor, but if you remember from the ramp wall lectures, the masonry walls are stiffer than the masonry fill. Because of this, load will first transfer to the walls, and only to the fill after the beam begins to bend and potentially crack. Finally, we can derive the equations for D effective and W effective using trigonometry. I've also added dimensions D1 and D2, which will be important later. D1 is the distance from the compression side of the beam to the centroid of the tension steel, while D2 is the distance from the compression side of the beam to the centroid of the compression steel. And you can see D effective and W effective are just a calculation based on trigonometry to calculate that largest rectangle I've drawn here in red, overlaying the anchor drawing. And while setting up the loads, we have two options. We can approximate the anchor as a simply supported beam or as a fixed end beam. Both with a uniformly distributed load, W, that is the combination of our earth pressure and cable forces. Because we cannot guarantee the positive transfer of moment at the supports, we will analyze the beam as both. A simply supported beam, as you can see, will have a higher maximum moment. However, a fixed end beam has both positive and negative moments, necessitating steel rebar on both sides of the section, which we do have in each of our standard anchor beams. In the next lecture here, I'll go into specifically the loads on the anchor beam. And in this diagram, you can see, we'll calculate those loads based on both simply supported and fixed, but our simply supported maximum moment is our WL squared over 8 with a maximum shear of WL over 2. Remember that L is our unbraced span, and our W is going to be a distributed load approximation of our cable forces. So we'll take the sum of our forces and divide by that unbraced span L to get our approximate distributed load. And then for our fixed load, you notice the maximum moment actually occurs in the negative direction. So it occurs bending in the opposite direction as our simply supported beam, and that's WL squared over 12.